Hey, my name is Jared. Today we're talking about basically the anatomy of a synapse, as well as a couple items of interest like capacitance, time constant, and length constant. We'll get to those in a second, but let's start with kind of the anatomy of a synapse. First off, a synapse will have a axon terminal and a dendrite, or rather a presynaptic terminal and a postsynaptic terminal. And this axon terminal will be depolarizing as it moves along this axon, right? And once it gets to about this terminal, it'll open voltage gated channels for calcium and other ions, but for calcium, which will activate snare proteins. So within this axon terminal, you have neurotransmitters within vesicles. And these neurotransmitters are going to be snatched up by these snare proteins, and these snare proteins are going to help exocytose these neurotransmitters into this synaptic cleft between the two terminals. With that said, you're also going to have transporters which will move neurotransmitters through and just kind of sit in the cleft and help us depolarize this dendrite. Once the neurotransmitters hit these receptors on the dendrite, you're going to have a response, or your receptor is really going to go through a conformation change in ionotropic receptors. That conformation change is going to open up or transform it into a pore so we can allow more ions into this cell body and propagate the action potential through. If it's a metabotropic receptor, then that's going to initiate a G protein cascade, and depending on which receptor you have excited or you've hit, then that can either excite or inhibit this cell body. Okay, with all that in mind, what do we do if we want to let's say stop the signal, or the signal's done and we just have leftover neurotransmitters either within the synaptic cleft or within the axon terminal over here? Well, what's going to happen is you'll have enzymes which will degrade the components of the neurotransmitter so that you don't accidentally fire an action potential in this postsynaptic terminal. This is considered a chemical synapse. In electrical synapses, like in your heart, you'll just have a pretty tight junction between cells, and there'll be connections which basically just they're all ionotropic. You allow ions to pass through really quickly. That's why the heart can pump simultaneously all the cells at once, because ions are just flowing so quickly. Okay, so now we've kind of covered what the synapse is, the anatomy of it, and how it all works, right? Let's move to capacitance, the time constant, and the length constant. We're back here with depolarization of a membrane. So let's look at this membrane, these two different membranes here. Sit down, see if, yeah, that works. So capacitance is basically the amount of charge divided by how much those charge contribute to a voltage. So in this scenario, we have a ton of charges, right? We have 4 positives, 4 negatives, a ton of charge between these two sides of the membrane. And on this side, we don't have as much, 2 to 2. The reason this is this is a high capacitance situation because you have a ton of charges, right? why is this possible? How can you put a bunch of like charges together super tightly? It's because you have a pole force between your positive and your negative that's super strong when your membrane is thin. Because it's so thin, this is strong, and it kind of negates these push forces that are pushing out. And because of that, you can accumulate a lot of charge on either side of the membrane. In this scenario, you have a thicker membrane. Your charges are spread farther apart, and so the pull force is not as strong, which means that these push forces have a little bit more power and they'll push away from each other. And that makes it such that you can't put as much charge onto either side of this membrane. These two different scenarios have the same voltage, but they just have different capacitance because their charges, just the thickness of the membrane doesn't allow it, or the thickness of the membrane plays very much into how much pull you can have to get those charges closer together. Let's look at the time constant. It's essentially the measure of how long it takes to depolarize a membrane, how long it takes to get positive charges into the membrane and into the cell, or through the membrane and into the cell. And this is dependent on our resistance of the membrane as well as our capacitance of the membrane. Let's look at resistance of the membrane first. If the membrane is really difficult to get through, it's going to take a long time for the membrane potential to depolarize. If that membrane really doesn't want that charge going through, it's just really difficult to get it to depolarize because you can't get positives into the cell. So that'll act as a multiplier. And then capacitance of the membrane, let's come back over here. If you have a lot of charges built up, if you have a high capacitance situation, it's going to take a lot of charges to get through the membrane to depolarize it because you have so much different charge built up. So if you have a high capacitance, that's a multiplier. It's going to take longer because you have more charges to move through. And if your membrane's super hard to get through, it still takes even longer. So your time constant is going to be longer, and it's just going to take longer to depolarize. Okay, let's look at the length constant. This is dependent on resistance of your membrane as well as internal resistance of the cell, kind of in that space. Let's go back to here. Let's say you have a you have membrane resistance, which you always have, right? But resistance internal, in this low capacitance scenario, you have less charges internal. So say you do get a positive charge through the membrane, its signal is not going to be negated by these negatives as much because you just have less charges there. So it's going to have a sphere of influence, kind of like this. There's your positive. It's going to have a sphere of influence that travels farther because it's less influenced by these. If you take a positive charge and put it in this situation, you have a lot of negatives that might weaken your signal, so it can't go as far. As well as resistance of the membrane. If it's hard to get through, then your signal is just not going to be as strong. So in the case of thicker membranes, like in a myelin sheath, you have a low capacitance, you can get a signal through farther, you have less internal resistance, it's going to travel farther. So yeah, I think that's it. Those are just some things to keep in mind when we're depolarizing a membrane and how a signal is going to pass through. And it all comes down to capacitance, time constants, and length constants. So